Yes, sir.
Visible, na? Acha, today the quiz is 6 p.m. That is there. Regarding fifth quiz, you have heard about it? Any notice for fifth quiz? I have heard it will be something like assignment or something like that. Have you
Yes,
heard
sir.
anything?
Yes, sir. We have. Yes, sir. We have heard it. Not officially, but yes, sir. We have heard it that it will be an assignment of 10 marks.
It will be an assignment, na? Okay. After this class, I'll discuss with the section B teacher. Right. Then 12 o'clock we'll decide it. Okay. What will be the whether quiz or something else? I think it will be decided by the department wise. Right. So in the department, yesterday department meeting was here. I absent, but anyway, after this class, 11 o'clock, I'll discuss discuss the matter with section B teacher Soumya, and then I'll inform you at 12 o'clock what will be the process, whether
Yes,
quiz
sir.
or assignment or something else. Okay, but today quiz
Yes,
is
sir.
fixed.
Updating in the group, sir.
बोलो बोलो क्या बोल रहे हो बोलो.
सर जो भी info आएगा वो group पे बता दीजिएगा वही बताएगा.
हाँ हाँ वो जो व्हाट्सएप में बता देंगे. ऐसे 12 बजे ही बता देंगे. अब नेक्स्ट क्लास जो है ना रेगुलर क्लास में, उस क्लास में हम लोग डिस्कस कर लेंगे. उससे पहले डिस्कस कर लेंगे सेक्शन पी टीचर से, और जो फाइनल डिसीजन है वो हम बता देंगे. ठीक है. और अगर डिले होगा तो फिर व्हाट्सएप में बता देंगे. नेक्स्ट वीक आई विल बी आउट ऑफ स्टेशन, सो नेक्स्ट विल बी whatever things everything it's not possible for me to give. I mean, it will be next week. But if okay, I'll try. If assignment is here, then I'll try to give the some assignment. That will be easy one. Anyway, I'll just inform you at 12 o'clock. Just a minute. Hello. Ronak.
Yes, sir.
I'm audible?
Yes, sir.
Okay.
Yes, sir.
Okay. Take it. Slide also visible, na? Slide visible,
Yes,
na?
sir. Yes, sir.
See, some problem. Today, Microsoft problem is here every minute, every hours. Anyway, last time I started this sonnet structure, sonnet HDH. These configurations we have discussed. This sonnet configurations is used in optical networks. Right, synchronous optical network. I have discussed it. And sonnet levels are used particularly in US. I told you, but in India, other than US, it is HDH. Right, synchronous digital hierarchy. Right, and we have seen the sonnet. It's a 90 column format. The most basic one is called the STS. That is STS, synchronous transport signals. Right, and the frame period, it is for this frame period, it is frame duration, it is 125 microsecond. Right, and if you know this, the columns and rows, 90 column format and 9 rows are there, so you can calculate the transmission rate. I told you. So it is 51.84 Mbps. Right. So if it is NSTS1, the basic one, so if it is STS3 or like that, it will be 3 times of that once. Right. But when this electrical, this is actually this is the format for digital time dilation multiplexings. And when it is used to modulate the source, then it is actually termed as OCN, optical carrier N. And different OC, you see, OC levels are there, OC1, OC3, OC192, etc. Today we'll see how this say sonnet levels OC192 it is used to interconnect the different cities. That I'll just show you today. And equivalent HDH, you see HDH hierarchy. These are actually STM1. These are termed as STM1. STM1 is corresponds to 3 times of STS1. So STS3 that is actually in STM1. That is in SDH it is STM1. So accordingly levels are. specified. Okay, this sonnet frames we have seen last times. It is used in it is sonnet rings, right? And sonnet rings it is not widely used in optical networks. Of course, trend is also there for RON networks and mesh networks, right? You see it here. When you use the ring sonnet rings, and then you should know the characteristics of the rings. There are three characteristics are there. There can be it can be 2 or 4 fibers between the nodes, and signal can propagate clockwise, anti-clockwise, and both line switching, path switchings are possible. So, and I told you what is line switching, what is path switching. Line switching means when link failure is here, the whole signals will switch to the another fiber. In path switching means within subchannels, signals are transferred. Subchannels, say OC12 may consist of several OC3. So any path failure is here, then the signal can switch to another OC3, like these things. So that is path switching and resilience. And we have seen last times the two widely used sonnet rings, UPSR and BLSR, unidirectional path switch rings and bidirectional line switch rings. First one consists of 2 fibers and second one consisting of 4 fibers. And in UPSR, you see it here, there is a protection path, primary path, protection path is here. And if any path fails or any node fails, then still that particular node will receive the signals from the protection path. Right. So here it is. This is shown here. Dotted ones, the protection path. So if say example is if path 2 fails, then still node 3 will receive the signals through the protection path. So that is the UPSR configurations. And these are actually self-healing rings. Initially, it is mentioned. Sonnet rings are self-healing. Automatically, it can overcome the failures. And in BLSR, consisting of bidirectional line switch rings, here more versatile capacity advantage is here, right? And in this case, 4 fibers are there. There also primary fibers are there, secondary fibers are there. There are whenever there is a protection fiber, secondary fiber, the protection fibers, protection loop. Both are bidirectionals. So if primary loop fails, or if any node failure is there or link failure is there, then you see how this you can see it here. If complete link failure is here, then the receiver, suppose if here it is node 3 and node 2, if complete link failure is here, then you can see it here. In a particular node, receiver transmitter will be there. So they will be internally connected, internally they will be connected, and that times protection fiber will be the primary ones, right? Protection fiber will be used, and in both cases, so node 3 and node 2. There can be a card failure also. In a particular node, there can be card failure. So if card failure is here you can see card failure, then it will switch to the protection fiber, right? Say here link failure is there. There can be card failure, there can be link failure, and the overall total link failure can be there. So then also traffic will not stop because of the bidirectional nature. So here actually more versatile in the sense one half is completely independent of the other half. So that's why it is more versatile than the UPSR. So these are the distinct advantages of bidirectional line switch rings. Next, you see how these sonnet rings, different sonnet rings, are interconnected in different scenarios to cover the backbone of the optical communications. Here, in this case, you can see different configurations are there using different types of sonnet rings. UPSR, you can see it. First, you can see the OC192. OC192, that can be a national backbone 4 fiber. So just we have seen this 4 fiber. You see very high speed capacity is here. So here it can be the national backbone, right? Or maybe also can be one continent to another continent also. So if you consider a particular country, that can also be there. It's a national backbone, and OC 48 rings that can be to intercity. That can be attached. A number of OC number. This is one ring. It is showing it here, but several such OC 192 rings can be attached with the other ones with this loop, with this various high capacity loop. And this OC 48, it can be say it can be one city, there can be another city, like these things. So OC 48 rings can be attached, a number can be attached in different cities. So different cities can be interconnected through OC 48 rings. Again, you can see here UPSR is here. It's a comparatively low capacity. This can be in industry or in buildings, like these things. There can be linear chains, also there can be ring also, right? So this can be within the buildings or can be industrial belt, like these things. So they are the low capacity SONET rings, right? So there can be inter-building or intra-building communications would be there with these low capacity channels, OC3, these rings, OC3 rings. So several OC3 rings can be interconnected with this OC48 through linear chains, or can be directly to OC48 rings. So these are the different SONET rings that will form the network architectures. And here you must keep in mind here each ring has its own failure recovery mechanisms and network management procedures. So this is large SONET network connecting different linear chains as well as different interconnected rings. Right, so it's a large SONET network. Large SONET network. Right. Next, you see in SONET also add-drop multiplexer is used. We have seen this add-drop multiplexer is fiber bracketings. So that type of add-drop multiplexings can also be connected with the SONET rings. Here it is shown here how different add-drop multiplexers are used to drop some wavelengths to add some wavelengths within the rings. Say here input stream is one OC48. OC48. This is the rings. OC48 ring. Right, and when and this OC48 rings, there are several subchannels are multiplexed. It will form the multiplexing of OC12, several OC12 and OC3 subchannels. OC12, these subchannels are there, are multiplexed to get these OC48 rings, OC48 channels, right? And this is OC48 ring. A part of it is shown here, and here you see ADM can be a part of these OC48 channels, right? And if you see it here, here you see OC12, the solid lines, the OC12s, and the dotted lines are OC3, right? OC12 and OC3 channels are passing through this ADMs entering, and after entering, you can see it here. OC2, OC3 channels are dropped. Two OC3s are dropped from these fast ADMs. after multiplexings. Then you can see it here, two OC12s and one OC3. This is solid means OC12 and one OC3. OC3 are added. How these are added, we have seen this using fiber bracketings, you have seen it. This is showing the block only. So two OC12s, OC3 are added again within this OC48 streams. I mean, it is added in such a way that aggregate will be OC48, right? So this OC48 again, it is transmitted through this ADA through the another ADMs. In this way, here some more sub-channels can be added, right? And another ADMs, some other sub-channels can be, the same sub-channel can be dropped, or some other sub-channels within the OC48 can be dropped like these things, right? Or it can be added also, it can be dropped also. So in this way, you can have the multiplexing. I mean, in the downstreams, you see channels can be dropped or can be added. Okay, so this is the SONET add drop multiplexers, add drop multiplexer for SONET configurations. So within this, within a mainstreams, some of the subchannels can be dropped or some of the subchannels can be added. Right. So also SONET can be used for multiple wavelengths. I mean WDM systems. In fact, DWDM systems also it is very useful. DWD systems in SONET rings. You can see it here. This is a DWDM systems. In this configurations, you can see high capacity OC92. This OC92, you see this stream is there. This trunk line is there. So several OC092 of different wavelengths can be multiplexed and can be transmitted through the fiber. Right. So here you can see it here several OC192. You see these streams are multiplexed through variable alternator. Here means it is variable alternator. Variable attenuator. So these are used to make the equal power of all the streams. Before multiplexings, they are used to these variable attenuators are used to equalize the output powers. Right. Next, they are transmitted through the fiber. But before transmission, after the multiplexed, so WDM also we have discussed. It can be a combination of plane splitting, or it can be interference filter type, indicator optics type, can be prism also, like these things, micro prisms. So there are different WDM components are there. So after this, there can be amplifiers, optical amplifiers. Post amplifier, it is there to increase the power. Inline amplifiers will be there to compensate the loss, and pre-amplifiers can be used to balance. Pre-amplifiers used to increase the signal to noise ratio, right, before the demultiplexers. So in this way, you see, it can adopt the WDM scheme also. The SONET rings can be used for DWDM cases, dense urban division multiplexing. So this is the configurations for the DWDMs in OC trunk rings. We have seen the OC rings are there that can be of multi-wavelengths. So this is yes, it is DWDMs, dense urban division multiplexings in OC192 rings. So we have seen these 192 rings are there. You can see here 192 rings. This is 192 rings. They can be of different wavelengths. They can be operated through different wavelengths. So that is the DWDM systems in OC 192 rings. Okay, so this is all about this the SONET frames, SONET rings, and ADDROP, and also how the SONET network is used for the backbone purposes, communication backbone. You see, so nowadays the networks you see are all optical networks, right? And all optical networks are required to make it versatile. I mean, communication network, if you see, they must. We have discussed it. If it is not all opticals, then you see the speed will be less. So versatile networks, generally communication network, are based on these all optical networks, and they must be of WDMs networks. So we can say all optical WDM networks they form the communication networks. All optical WDM networks are used in communication networks, right, to make it versatile. And where the type of the all optical network WDM networks are used, in particularly in LAN, local area networks, it is used. And this is called actually broadcast. These all optical networks can be broadcast and select networks. These are called actually broadcast and select WDM networks. So all optical networks actually count as broadcast and select WDM networks. This, I mean, WDM is used to make it more versatile. That just we have seen it. Commercial advantage also we can have it because of these different wavelengths, multi-wavelength systems. Again, these broadcast select WDM networks, this can be also of two types. It can be single hop, it can be single hop, it can be multi-hop networks. In single hop networks, a single hop that doesn't mean single wavelengths. It can be multi wavelengths. All are multi wavelengths, but it can be single hop or it can be multi hop. Single hop means from source to destinations. There will be no optical to electronic conversions, and there will be no conversions, right? Source to destinations, but set of wavelengths can be used. So information transmitted, you see here in case of single hop networks, transmitted without converting the electrical forms to any intermediate node, right? But in case of multi-hop networks, the reverse is here. Here you see intermediate node, they performs the electrical to optical conversions, optical to electrical, electrical to optical conversions. So that's why it is called multi-hop networks. So in multi-hop networks, there will be electrical to optical conversion is here, but in single hop network, there is no such conversions between source to destinations. So you see the examples that are more clear. Here you can see it here. This is the star configurations. This is star, and this can be this is a bus configurations. You can see it here. Here, say different nodes are there. This is node 1, node 2, etc. And each node, there is a transmitter receiver is here, and there is a star couplers. So here, each node there is a particular wavelength transmitted. And see this one, but here the each node receiver of each node will receive all the wavelengths from all other nodes. Each receiver will receive all the wavelengths transmitted by each node. So this can be in star configurations. It can be in the bus configurations. You can see it here. In the bus also, all the wavelengths are you see are loaded in the bus. All the wavelengths, right? So in the receiver, all the wavelengths are received at a time. But to receive, to get the information from a particular wavelengths, it must have a filter. Right? It must have filter. So in this case, you see, it can be, there must be a tunable filters, so that it can tune to a particular wavelengths that is addressed to it. Say particular receiver, not necessarily a particular node sends some information to a particular node, then through through particular wavelengths. So the particular receiver, you see, it is expected to have that particular wavelength. So to get that particular wavelength, it must have tunable filters, so that it can tune to that particular wavelengths. And so each at a time, each receiver will see all the wavelengths. But you see, because of this tunable filter, it can receive only, it will receive only one wavelengths. So that you can say it is a kind of drawback also. Right. You must have it must tunable filters is very costlier affairs. Anyway, but this can we start with us, and this is this single hop network. It can be, this is single hop network. There is no conversions, operating conversions, right? And you can see it can be this thing. It can be this. It can be multicast or broadcast also. Not necessarily, but node to node 1 to node 2. A node 1 can transmit more than one node also. So it can be multicast or broadcast. Can be one node can transmit all other nodes, or a particular group of nodes. That is multicast, and the last one is the broadcast. So in these examples, you can see it here. Says node 1s. You can see it here, node 1. It transmits the informations. Through lambda 1 to node 5 and node 3. You see, it is through lambda 1s, right? But node 2 to node 4, you see, that is used the lambda 2. So it can be broadcast also, it can be multicast also. Right. This is single hop network. Keep in mind, this single hop networks. Right. And here you see different wavelengths are there. So here one thing you should keep in mind, this here protocol transparency is here. I mean, different communication nodes, they can use different protocols. They can use different protocols, right, without affecting the other nodes in the network. So protocol transparency is here in WDM systems. Right, but here the disadvantage is there must be dynamic coordinations between dynamic coordination here is mentioned. You see, dynamic coordination is here between the source and between the nodes, source and destinations. I mean, here the receiver must be informed when a message is sent to that particular receiver, and then it can tune to its tune to that particular wavelengths. Right. So that means coordinations must be established. Right. Some message must be sent so that it can tune, the receiver can tune to that particular wavelengths. And generally, message can be exchanged. Also, this is one drawback. Another drawback is there can be conflict. Suppose two stations are there. Two stations, if they transmit the information to the same receiver, then there can be conflict. Right? Simultaneously, there can be conflict. So conflicts can be there. If two stations at different wavelengths send the information to the same receiver simultaneously. So that is the conflict case. So the two things are there. So that the limitation of this single hop network. There must be dynamic coordinations between the nodes, and there can be conflict when the two stations transmit the information to the same receiver simultaneously. Right. Well, this drawback, of course, can be overcome in case of the multi-hop networks. In multi-hop networks. So this is basically broadcast and select networks. So broadcast and select, I told you earlier, broadcast and select network can be single hop network and the multi-hop networks. And the most important thing is this in single hop network, the costlier thing is this tunable filter or tunable lasers. Those things are there, but those things can be avoided in case of also the conflict. Those things, these things can be avoided, can be overcome in multi-hop networks. So in the examples, you can see it's a 4-node. It's shown here. A broadcast and select is a multi-hop network. This is this one. This one. Carefully, you can see it. This is a multi-hop network. Here, if you see it, each node transmits a set of wavelengths that is fixed. Say node 1, it transmits, it sends information to two particular wavelengths, not all the wavelengths. Two specific wavelengths are there, lambda 1, lambda 2. So it transmits information to the only through these two wavelengths. Also, it can receive the information to the other two wavelengths, which is lambda 5 and lambda 7. So if suppose lambda 6 is there, it will not receive, it will not detect. So that a particular set of wavelengths is there for transmission, and a particular set of wavelengths is there for receiving the informations. Right. That is true for all the nodes. So node 2 also, it is lambda 6, lambda 8 for receiving the informations, and lambda 3 and lambda 4 for transmitting the informations. Right. Similarly, for node 3, you can see at lambda 3, lambda 1s receiving the informations, and lambda 5, lambda 6 for transmitting the informations. Right. You can see it here. Suppose in this case, so the conflict, everything, those will be avoided here. Suppose if node 1 wants to transmit information, want to send information to node 2. Node 1, this node 1 to node 2. Node 2. How it can send the information? You can see it here. First, it will transmit the information to node 3. Through this couplers, you can see to node 3. That will be through common wavelength is here, common wavelength say lambda 1. Here lambda 1. So node 3 can transmit lambda 1 and node 3 can receive lambda 1. So node 1 transmit informations to node 3 through lambda 1s. Right. Next, node 3 forwards this message, forwards this information to node 2. Now you see how node 3 and node 2 is interconnected. That is interconnected through lambda 6. You see it, lambda 6 is common. It can transmit lambda 6, it can receive lambda 6, node 2. Node 3 can transmit lambda 6 and node 2 can receive lambda 6. So node 3 will send the information, same information through lambda 6 to node 2. So in this way, informations are exchanged between the nodes, and you can see that there will be no conflict or collisions of packets in each channels. Right. So there will be no collisions in the network. So one thing is here in multi-hop networks, here particular wavelength is dedicated to a particular source to destination link. Just now I mentioned node 1 to node 2. Node 1 to node 3, it is dedicated channel is here, that is lambda 1s, and node 3 to node 2, it is lambda 6. So a dedicated wavelength channel is here for a particular source to destination links. But also, so here multi-hop is here, but single hop is not going to the single hop. So first it will go to the node 3, then node 3 to node 2. So number of hops will be there. So if there is certain number of nodes are there, obviously there will be so many hops will be there. And so for each hops, you can say the throughput penalty will be there. For each, if there is each number of each hops for a particular communications, each hops is there, then network throughput penalty will be 1 by h. Right. And another things are there, you can see. And here data packets, if you see the data packets in multi-hop networks, you see it contains the header information packet. And in the header, you can see it, source identity is here, destination identity is here. Other contributors would be maybe there. So, so intermediate node, intermediate node in this case, multi-hop network, the optical signal is converted to electrical signals, and then header you can see header, it contains the source identifier and destination identifier. So header will indicate where the packet will go, right? Because of these informations, identifications, source and destination identifications. So using this type of format, the packet is then switched to a specific transmitter. Electronically, it's a specific. First, you see any node, the receiver transmitter is here. So first, it converts optical to electrical. Next, electrical signal will be transmitted to through the transmitter. It will again convert to electrical to opticals. Right. So the node will direct the packet to the next node. Through the established logical paths.